Welcome, everyone. Thank you all so much for joining. It's nice to see some familiar faces and some new people. We're just going to give everyone a minute to arrive at the Zoom, and then we'll go ahead and get started. Okay, thank you all so much for coming. CITP is an interdisciplinary community. I'm happy to see some new people at the talk. So let me just briefly provide some ground rules before I introduce Pranay. So in terms of format, Pranay will give a talk for about 45 minutes, and then we'll have some time for questions. If you have any questions during the talk, questions of clarification, please put those into the chat and I'll moderate those. And then at the end, we'll turn to more in-depth questions and discussion. So that's a little bit about how this seminar works. And now it is my pleasure to introduce Pranay Anchuri. So Pranay is a data scientist at CITP. He received his PhD in computer science in 2015 from Rensselaer Polytechnic Institute. While in graduate school, he worked at various industrial research labs, including IBM, Yahoo, and QCRI. He comes to CITP most recently from Anchuri, which was in New York, doing high performance permission blockchains. Pranay's been at CITP for a few years now, and he's been a real wonderful addition to our community with his curious mind and bringing in fresh skills and perspective. And so it's my pleasure now to turn the floor over to him so he can share some of his research with all of us. So welcome, Pranay.
Thank you, Matt. Thanks for the introduction. I'll share my screen now. Can you see the presentation?
Yes, thank you.
And can you hear me okay?
Yes.
Okay. Yeah. Hello, everyone. Thanks for joining. I'm really excited to talk about the insights into predictability of life outcomes. This is a joint work with Emily, who is a PhD student in the sociology department, and Matt. So let's get started. So the main topic for the talk is about the predictive analytic tools for social policy. In recent years, welfare agencies throughout the world, mostly in the developed countries, are increasingly relying on predictive analytic tools to help improve or replace human judgments, which are potentially biased. This has seen applications in criminal risk prediction and improving assignment of resources to the communities of need. A recent example is the predictive risk modeling tool that was deployed by the Allegheny County in Pennsylvania to improve child welfare call screening decisions. So this is a call center that receives calls about maltreatment for children, and this system augments the decisions of the humans in that call center. Recently, there was a study by ACLU on the such tools that were used in other states and counties. They've noted that at least 26 states have started using or exploring such tools for child welfare. Before these tools are deployed to the wide public, there are many issues. For example, like the legality of these or the ethical aspect of these. But what we are interested in is a more basic question of how accurate are these tools, whether these tools can predict the outcomes that are important. So we are looking at like the fundamental question of are machine learning tools applicable in these predictions. So to do that study, we need a high quality data set. One such data set is Fragile Families and Child Wellbeing Study data set. It is a longitudinal survey data that started in year 2000. to study families formed by unmarried parents and the lives of children born into those families. It has surveys and in-person interviews, and it tracks the lives of children, caregivers, and parents at various stages of life. So here I show these interviews are conducted at birth to all the way to age 15. And these are some of the topics that were covered at those time periods. This dataset is ideal for studying predictability because the data is collected after informed consent and has an IRB approval. It is used in more than 1,000 academic papers, but most of these papers are focused on a specific variable that is tracked, but there are not many studies that look at the predictability of outcomes that we are interested in. And another important quality of this data is the availability of high quality metadata, which is all the information about like what kind of topic a particular variable is, and there's a entire dedicated team that tries to constantly provide updates to the metadata. So using that data, there was a recent study which is called the Fragile Families Challenge. It used a common task method, so where where teams work on a common problem, and the problem here is to measure the predictability of 6 outcomes that were part of this data. So this is similar to the Netflix challenge, which had like $1 million prize, but here there was no monetary value to it. So the data is like this. So there's information about around 4,000 families. The goal is to predict 6 of the outcomes at age 15 based on the information from birth to age 9. All the teams had access to the entire background data, which covers information about their health, their education, and all the topics that were covered during the survey. And the teams included researchers from a variety of fields and career stages. So if we look at after the challenge ended, we learned several new things about the predictability of these 6 outcomes. Before looking at that, all the submissions were compared using the R-square score metric. It is simply 1 minus the ratio of mean squared error of the prediction submitted by the team divided by the mean squared error if they had predicted the mean of training data. And this value is never greater than 1. A value of 1 implies a perfect prediction where there's no errors. A value of 0 implies that the predictions that we make are as good as predicting the mean of the training data. And a negative R-square implies that we are doing worse than the mean. So with that background, the graph here shows the R-square score for 6 of the outcomes. The results are quite surprising, and because we usually expect with such high quality data and a lot of variables, we can predict anything. But what this challenge has shown is, even though you have a lot of teams competing with high quality data, they are barely able to beat a simple model that predicts the mean of training data. So you see like the 4 variables where the R-square score is quite close to 0. Moreover, they also compared the R-square score against a simple benchmark model that is based on a regression of 4 variables selected by a domain expert. And all the fancy machine learning algorithms and pipelines, they are slightly beating, but not by much. So we wanted to learn what if we do this for many outcomes, like all the outcomes that were chosen in the challenge were 6 out of 1500 outcomes. But can we learn, what can we learn by doing this on much broader set of outcomes? So as I mentioned, the challenge is only for 6 variables. So there, one thought would be to use the submissions from the challenge because they open source their code and just run it on all the 1000 or 1500 outcomes. But there are several issues in doing that. One is the submissions didn't require a reproducible code. And the second is, in some cases, the teams have used specific techniques tailored for specific outcomes. So we cannot use that for other outcomes. Moreover, we want to learn the differences in the predictability, like why one team is doing better. And if we want to compare that, we have to, it's difficult to compare if the teams have not used a common template. So to solve these problems and study the broad question of predictability of life outcomes, we created a computational framework from scratch for studying predictability of outcomes. So the basic idea is most submissions in the challenge followed a 3-step approach, which is the standard data pre-processing, feature selection, and statistical learning. So we looked at what kind of methods people used in the challenge, and then created thousands of learning strategies by creating unique combinations of these 3 steps. So we take the types of statistical learning methods, the types of feature selection, data pre-processing techniques used in the challenge, and create thousands of learning strategies. We call these ML pipelines. And we use these pipelines and the framework to create kind of a simulated mass collaboration similar to the challenge, but for all the outcomes at age 15. So before going into the details of the framework, I wanted to tell more about some of the design considerations for in building the computational framework. One is we wanted this framework to run both on a local machine or on cloud. Then we also want to make it highly scalable, so that it exploits parallelism that's inherent in this problem for high performance and scalability. We also focused a lot on quality right from the beginning by having automated end-to-end tests and detailed issue tracking, changelog, and tagged releases. Another important aspect of the framework is the reproducibility. This was always a key design principle for us. So we made sure that the configuration used, the code base, and the results are always linked, so that we know which code is corresponding to which results. And we also have automated tests to ensure reproducibility of the result. And for the data, we made sure that there are no hidden pre-processed files, and we also ensured the data versioning of all the files used. So looking a bit more into the architecture of the framework, I won't go into a lot of details, but the basic idea is we create a config file that's shown here. This is usually all the team members. We decide on what scientific question that we want to study and design the configuration for that. And we have the data. Then this is sent to a machine that creates these tasks that are eventually run on a cloud on a cluster of machines. After running all these machine learning pipelines, the results are stored on a different server where we host some dashboards and other analysis scripts. So looking more into the pipelines, as I mentioned, our pipelines are combinations of these 3 steps. And specifically for a single pipeline, we have the raw data that goes through data preprocessing and feature selection. Then it goes through the statistical learning step, and finally it gives out a tuned model. And the pipeline combinations that we use depend on the outcome that we are trying to predict. And moreover, we have, if the models have hyperparameters, they're tuned by a cross-validation. Here is a simple calculation on the scale of the experiments that we are running, which is not very common in the social science field. So that's why scalability is a key thing. So we have 1,000 outcomes. We do 5-fold cross-validation, and we have around 1,000 learning strategies. So in total, we have 5 million outcome pipeline combinations to run on the cloud. To give some more numbers, it takes more than a day on 5 machines that each has like 64 cores. So in terms of dollar amount, it's more than $1,000 per a single run. So it is quite unusual in the social science field. All these pipelines are described in a config file. So whenever I talk about predictability, it is the R-square score that I defined earlier among all the pipelines that were used for this for an outcome. So we take the maximum of all the learning strategies. So with this framework, it enables us to study what would have happened if through these mass collaborations. And our computational framework provides a nice opportunity to study the impact of various pipeline steps, be it the modeling or the data, and its impact on the predictability of the outcomes. So today's talk is mostly about the impact of various pipeline steps on the predictability of outcomes. More specifically, we look at the impact of these 3 steps here: the hyperparameter tuning, the impact of what machine learning technique is used, and the data that goes into the model. So the first question that we try to answer is, does predictability depend on hyperparameter tuning, and to what extent? The second question is, does predictability depend on the statistical learning method that's used in the pipeline? And the third is, what is the impact of data that goes into the learning method here? We are also doing other studies. Emily is leading some of them. They are mostly about looking at what kind of topics, like what kind of outcomes in terms of which topics of outcomes. Is education more predictable, or is sexual preference more predictable to other topics. So we are doing other studies related to that. So with that background, I'd like to jump into the 3 studies that we started to do. So the first question that we want to answer is, does predictability depend on hyperparameter tuning, and to what extent? So in it, the first kind of major release of our computational framework didn't have used the default models that were available in scikit-learn, like models with default parameters. And this is the R-square score distribution for the 1,000 outcomes. The results were quite surprising here. What we see here is most of the outcomes have a negative R-square. That means even though we have all these thousands of learning strategies, we are not doing better than simply predicting the mean, which is a major negative result. However, we know that most practical machine learning deployments, usually like in industry, they are tuned for a specific data set or the problem in hand. So more specifically, this is the problem of hyperparameter tuning. The basic idea is most of the machine learning models are sensitive to some of the internal parameters. These are like knobs for these methods, and it has to be tuned in a certain way for it to perform optimally. An example of that could be the depth of the tree for decision trees. And as I mentioned, tuning refers to the process of optimizing these knobs. And it is known that the effect of hyperparameter tuning varies a lot by the parameter that is tuned. Like some parameters are very sensitive, and the others you're better off, you can just use the default values. And most library authors use set the default values based on a combination of intuition and by running experiments on many data sets. So now we look at what is the impact of hyperparameter tuning. To do that, we tuned all the learning strategies that were used in the pipelines by using a random grid search for 256 iterations in a 5-fold cross-validation step. And this is the distribution of R-square scores after doing the hyperparameter tuning. So the green the green distribution here shows the R-square score after tuning. We can observe several things. One is the mean has improved from negative to slightly above 0. Moreover, the 95% confidence interval is between 0.03 to 0.06. And the median has also increased from negative to the positive region. And we also performed statistical tests to ensure that the mean or median of the difference in R-square score is not 0. So what this shows is there's a statistically significant improvement by doing the hyperparameter tuning. So we explored this a bit more by measuring the absolute impact of hyperparameter tuning. So to do that, we compute the difference in R-square score for the best tuned model out of all the learning strategies, and the best default model, that is without using any hyperparameter tuning for all the outcomes. So here, the x-axis is the difference. So positive is better. That means tuning is better. And this is the number of outcomes. What we see here is around 85% of the outcomes, if we take the best values, they have improved by doing hyperparameter tuning. So here we don't see this by the specific model use that we see in the upcoming slides, but this is the overall impact. Like if we pick the best learning strategy for each outcome, around 85% of them have seen a positive improvement. So before looking into the how hyperparameter tuning impacted on models, the way to look at that is like if we do a scatter plot with x-axis, the R-square score with the default values, and y-axis as the R-square score after hyperparameter tuning, then everything above this x equal to y line is positive improvement. And moreover, the line y equal to 0 is the baseline that is predicting the mean of training data. So what we are looking at is, what we want to find is points in the green regions where the R-square score before was negative, but after tuning it became positive. So now we see the impact of hyperparameter tuning on each of the models. So here, if you look at this graph here, it shows they're all in the improvement area, and there are some points in the second quadrant that is the best location for us to be. Another way to look at that is by measuring the mean, the distribution of improvements for each model. Here we see for each model what is the mean improvement in R-square score. What we observed from this graph is that out of 6 out of the 12 models that we used have a statistically significant improvement, like a non-zero improvement. In general, tree-based models, that is the extra tree regressor, decision tree regressor, AdaBoost, they all seem to be improving in general. And surprisingly, support vector machines don't have much improvement in this data set. So so looking back at the question, we started out what does predictability depend on hyperparameter tuning, and we noticed we learned of new things here. One is the R-square score improved for 85% of the outcomes. There's statistically significant improvements for half of the models, and in general, tree-based methods seem to benefit the most. That's the end of the first question. Then now we go into the second question, which is, does predictability depend on the learning method used? So if you remember, like the 3 steps that we wanted to focus on, we looked at hyperparameter tuning. Now we look at the specific learning method that is used. So to do that, we first do a head-on comparison of models. So what we do is, keeping everything else constant, what if I change one learning method to a different learning method? Then we compare the R-square scores in both these cases and see how many times a model wins against the other model. So here it's a heat map where each cell shows how many times model 1 wins against other models. The pattern is pretty clear here. AdaBoost regressor seems to beat most other models in most of the times. And we also perform statistical significance tests to basically check that there's a significance difference in the models. Another way to look at this model comparison is by doing ranking of these models. So for each outcome that we are interested in, we rank all these 12 outcomes in terms of the R-square score. And the graph here shows the distribution of ranks for each of the models. So lower rank is better. So rank 1 is the best performing model. So as you can see, AdaBoost has a median rank of 1. That means in majority of the outcomes, AdaBoost is the best performing model. So another way to say this is if you are restricted to picking one model, you are better off going with the AdaBoost regressor. And another interesting observation is the nearest neighbor regressor does surprisingly well, even beating the multi-layer perceptron after tuning. Then we also looked at in which regions of predictability these models are doing good. So what we see here is interesting. So we here on x-axis is the maximum R-square for the outcome. On y-axis is the number of times a particular model is the best performing in that region. So we see that AdaBoost regressor that we saw earlier to be performing good is the best only when the outcome is less predictable, like when the R-square score is closer to 0. Whereas the XGBoost regressor shown at the bottom right seems to be doing better when the R-square score is higher. So when the outcome is more predictable, XGBoost is better. Whereas if it is not very predictable, then AdaBoost seems to be doing best in this data set. So that's about keeping everything else constant and varying the models. We looked at what are the differences in the ML models used. We found significant differences in model performance. And we noted that in general, AdaBoost regressor beats other models. That leads us to the third study of which is the impact of data that goes into the learning step. So we have looked at hyperparameter tuning and the machine learning model. Now we switch gears and look at what is it about the data and how does it impact the predictability. So some of the common factors that affect predictions or prediction accuracy in general are the number of samples. As you have more samples, you have the chance to fit a better hypothesis to your data. Then it's also about the quality of predictors and how well it correlates with the outcomes. And so instead of so we cannot arbitrarily push more and more predictors and expect a higher predictive accuracy. It's more about the intrinsic dimensionality So what is the lowest dimension that explains the predictor data? That's an important factor. So we wanted to learn what is it about the data that we are sending in and how it is affecting the overall predictability. And since the data can be described in many ways, we need a different approach to study this effects. To do that, we use meta learning to uncover features of the data that impact predictability. So some information about meta learning. So the main goal here is to learn from prior ML tasks to see how a particular ML technique has done on a previous data set in a more data-driven way. So the main ingredients for doing meta learning is we need to describe the predictor variables. So that is defined as the meta features. So in our case, it would be something like for each outcome of interest, which is for each row, we describe several properties. So for example, here we show the number of samples in that task, some R-square score with the benchmark model, and the number of outliers and so on. And we also have the R-square scores for each of these outcomes. So for each of these three outcomes, we have 3 R-square scores. And the goal of meta learning is basically to learn a function that maps these meta features that describe the data to the meta outcome, which is the predictability of an outcome. So all these meta features are only constructed on the data that goes into the statistical learning step. In other words, we don't look at any of the testing data at this time. More concretely, the set of meta features that we use are split into 5 different categories. One is the general descriptive statistics of the data, that includes number of data samples, types of attributes, etc. Then we have a bunch of statistical metrics that deals with the correlations of features to outcome. Then we have some computational complexity metrics. This includes the intrinsic dimensionality. Then we also have landmarks, which is the performance of a baseline model. This would be a performance of depth 1 decision tree or a 1 nearest neighbor regressor. And another important category of features is the features, the meta features that we built on the metadata for the that is available from the child well-being study. This includes the topics of the predictors, the missingness, and so on. So in total, so we have 1,000 outcomes and around 62 meta features to describe each of these outcomes. Before looking at the meta modeling step, I wanted to show some correlations between the meta features that we just constructed and the meta outcome, which is the observed R-square score. So the graph on the left here shows the complexity dimension of the feature matrix, which is how many dimensions of the input data do you need to capture 95% of the variance of the data. And what we observe is, as expected, if you have data that lies on a high dimensional space, you need more and more samples and more complex models. So in general, you expect lower R-square score at the scale of data that we are working with. Another interesting meta feature is if you look at what fraction of predictors are of the type constructed, or what fraction are of the type questionnaire. So all the predictor variables used in the dataset are categorized into one of these two categories, where questionnaire means that it is a question that was asked during the survey. So what we see here is if there are more questions coming, if there are more variables coming from the survey question, generally the R-square score seems to be lower. This could be because the quality of these variables is not as good as quality of constructed variables. So as you can see, each meta feature has different effect and to different degrees. So instead of looking at all these features individually, we want to see, given all these features, how well can we predict the meta outcome. So to do that, we fit a simple regression model that maps the meta features to the meta outcome. And this had an R-square score of 0.66. Now I'll show some of the meta features with statistically significant impact on R-square score. So these are the beta hats that are significant. So here we see quite a few meta features that have either positive or negative impact on overall predictability. So for example, the landmark model, which is the internal fit of a simple model, has a positive effect, whereas outliers, the fraction of samples that have an outlier has a significant negative effect. Another thing we notice here is that the topic of these predictive variables is also quite important. So some topics are more important compared to other topics. So as I mentioned again, number of outliers also has a strong effect. Internal R-square score is a good indicator. So even though some of these seem trivial, it's important, like when we put all of these together, what are some things that are uniquely responsible for the predictability. So looking back at this meta learning step, we started out to do what is to measure the impact of data going into the learning step on the predictability of the outcomes. So we noticed that outliers lead to a significant decrease in the R-square score. We also noticed that high quality predictors, such as the constructed variables, lead to an increase in R-square score. And internal models is a good indicator of how well we see on unseen data. So that brings us to the end of the 3 study questions. So again, we created this computational framework to simulate mass collaborations. And this talk is looking at 3 important steps and their impact on the predictability. So in summary, we created this framework. One of the one main thing that we can take away from this study is life outcomes are incredibly difficult, even with very complex machine learning pipelines. As we can see that the R-square score is quite low for many outcomes. Then studying the relative differences between these different learning strategies shows a lot of interesting things. One is quite important to do hyperparameter tuning, and the impact depends on the particular model. So, so the main learning here is which factors to which parameters to focus more on, because most of the parameter tuning is limited by the amount of computational resources. So this gives us information on where to best focus the budget of computational resources. Then we also compared all these different learning strategies. And what we noticed is no single pipeline consistently beats other pipelines. But we noted some models that are doing better than other models in most cases, like the adapose regression. Another interesting thing is the quality of data that goes into the learning step has a significant impact, because as we see, the Rsquare scores range all the way from +1, which is like perfect predictability, to negative values, and most of this could be explained by the quality of data that goes into the learning step. So that brings us to the end of the 3 studies and the conclusions. I'd like to take this opportunity to thank all the support from the CSML and for providing computing credits, and for my research through a gift from Schmidt Futures Foundation.
Okay, so then I think we'll go ahead and wrap it up. I would say that Pranay is, I'm sure, happy to take any additional questions over email, and he would welcome any feedback you have about the talk. I personally would welcome feedback about the talk as well, as would Emily Cantrell, who's on the talk, but in the library, I guess. So feel free to talk to any of us about this work, and let's all please thank Pranay again for a wonderful talk. Thank you so much, Pranay.
Thank you. Thanks everyone for joining.
Hi, everyone.
Bye.